So now we come to the next type of transistor, that is FETs or field effect transistors, where the first thing we learn is JFET. Now this is the structure of a JFET where we apply a drain to source voltage. So this is our drain, this is our gate, and this is our source. And that is how we make the transistor work. We will come to what gate, drain and source are very soon. But first we need to learn how this transistor basically works. The first thing is this works due to the effect of an electric field instead of the base current that we were working with earlier. So we are basically trying to get this base current to almost zero. Therefore, remember that base impedance that we were talking about in case of a BJT. This impedance in case of a transistor is in mega ohms, while in case of a BJT it was just several hundred. So sorry, this is several hundreds of mega ohms, while this was just about 1 to 2 mega ohm. So this allows much lower current through the base. So basically our input signal remains much less unaltered. This is much greater thermal stability, and also these are much smaller and can be used in ICs. Now, in a JFET particularly, the depletion regions are not uniform from the source, so this part, to the drain. And why this happens is because from the drain to the source, when we are applying a voltage, we basically get a resistor combination like this internally within the JFET. And what happens is that suppose you apply plus 2 volt and this is 0 volt, you basically get a very low potential drop across all of these resistors as you move down. As a result, what happens is that this alters the depletion region width of the surrounding p-type region in the JFET. And as a result, what happens is that the lower region is suppose reverse biased by only about 0.5 volt, while the higher up region will be reverse biased by about, let's say, 1.5 volt. And due to this region, the depletion regions, so basically this part, are non-uniform throughout the JFET. So the exact current we do not get. So throughout the entire structure, the current will not remain constant. Now we learn about the pinch off effect. Basically what happens is, after a certain voltage, so we saw that how the channels were non-uniform. So it is thinner at the base, so towards the bottom half, towards the source, and then it gets thicker as we move towards the drain. Let's just draw it neater. So something like this. And what happens is, after a certain voltage, these two channels basically merge with each other towards the upper half, and this causes a pinch off of the drain to source current that we were getting over here. So remember that resistor structure I was talking about, that current is now very low. And as a result, what happens is that if I draw the drain current with respect to VDS, so drain to source voltage, what happens is that after a certain point, the current will practically become constant. And this is known as VP. Here, this is almost a straight line. And this is due to the N channel resistance. And at this point, this appears as almost a straight line. This is also known as the linear or ohmic region of operation of the JFET transistors. And at this point, this is known as the saturation level, where VGS is 0 volt. This part is also called as IDSS, or eye drain saturation. Now in this curve, this pinch of voltage is actually the most important factor we need to deal with. Now let's say VGS was 0 volt over here. If we give VGS as, let's say, -1 volt, then the curve would appear something like this. And similarly, at let's say VGS is equal to minus 4 volt, the curve would almost be flat. Now, what is to be noted is the locus of VP is actually something like this. So keep this in mind that at the point you show the VP, this should intersect, otherwise the curve will be an upward facing parabola like this. So this is the locus of VP with respect to VGS. And of course, in this part, so basically if this is the curve, in this region, we have the ohmic region, and in this region of the curve, we have the saturation region of the GFET. Now plotting the drain current with respect to a drain current we know at a certain point, we can see that with respect to decreasing VGS, so this is 0 and this is suppose minus 4, we get lower and lower ID. Now if we were to plot, let's say over here VDS, then you know that we would have gotten a curve like this, which we have already discussed. So this point would meet, this pinch off point would also meet on the horizon. And similarly for a lower voltage, if we had plotted, let's say here we are getting ID is almost 0, then we would have also gotten these points to coincide. And these curves might be asked. Now structure of a MOSFET, follow this part very carefully. So first way to draw this is to remember that it mainly consists of two parts. So there is a P-type substrate and there is a silicon dioxide layer, which is also known as a dielectric layer. Remember, we learned this in case of capacitors. And through this dielectric layers, we have an N channel over here, another thinner N channel, and then another thicker N channel. So this will be your drain, this will be your source, and here will be your gate. Now keep this in mind, while the source and the drain are connected internally to the N regions, the gate is separated by this SiO2 layer to the P substrate. Therefore, there is an additional pin in the upper region of the MOSFET which is directly connected to the substrate. It is also possible for the substrate to be internally connected to this gate in certain kinds of MOSFETs. And the reason why this SiO2 exists is basically so that this gate only applies the required electric field for this semiconductor device to start conducting. Remember that SiO2 is a dielectric, so it opposes charge carriers and opposes the flow of electricity. Therefore, this offers very high resistance to this gate channel. So now the basic working of an enhancement type N channel MOSFET, and we will learn why exactly all of these terms are used. So first, when we give a sufficient VGS, the first thing to note is that nothing will move through this silicon oxide layer. Now what happens is, since we are giving a voltage over here, the holes in this P-type substrate are basically repelled by this voltage. So the holes get repelled, right? And similarly, since we're giving a voltage over here, the electrons are repelled by the N-type substrate. So there is a formation of a depletion region along the N-type substrates. So this is the first thing that happens. However, what happens is, as the holes are repelled due to this VGS voltage, similarly, the electrons over here will get attracted towards the gate. Now, after a certain amount of VGS, which we known as VGS threshold, or VT or VTH, which is the threshold voltage, we get the formation of a channel over here, which if you remember, I had already drawn in the original diagram. And this channel allows the flow of current from drain to the source. Therefore, enhancement, since this channel is formed by the enhancement of voltage, so positive VGS causes this enhancement. Therefore, the enhancement and channel, since this channel gets created and this is made out of electrons or negative charge carriers, so enhancement n channel layers. Remember that since this is only applying a field, these electrons won't be able to escape through the gate channel. Now, to learn the output characteristics of the curve, we get a very familiar curve to what we have seen before. So, this is the actual curve we are talking about, right? Now, keep in mind that as long as threshold voltage is crossed, we get these curves. But until it's crossed, we get all of the curves basically being a flat line very close to the zero current. And what happens is, as we start increasing the voltage, the curve becomes steeper at first and once again flattens out. What is interesting is, at this point, in this point of the curve, the diode works as a triode. I mean, the MOSFET works as a triode, and so it is known as a triode region. Triode is a semiconductor device, which is something else we will learn. Now, VDS saturation is the point at which the saturation drain to source current is obtained. And note that if we plot the locus of this VDS saturation comes out something like this. And towards the left of this curve is what we known as triode region, and towards the right of this curve is what we known as saturation region. Now, this is how you can easily remember what is the triode or ohmic region, what is the saturation region, and if the threshold voltage is greater than the gate to source voltage, then you will call that as cutoff region. So anything beyond the VGS is equal to VT curve. There's an interesting phenomena in MOSFETs which is known as channel length modulation. So if I just quickly show what happens is, remember when we had the N channels over here, I had shown a very thin layer of depletion region. What happens is that as we increase VDS, so drain to source voltage, this channel, so this depletion region basically thickens. And as a result, what happens is that this channel is effectively shortened. So L decreases. Now, ideally, this should not happen. So therefore, we need to change what current we get at higher VDS. So basically, the formula for ID is, for an ideal MOSFET, half mu n mobility of electrons, COX W by L, so width by length, channel width by channel length, VGS minus VTH whole square. However, since ID also starts to vary with channel length over here, we add this term 1 plus lambda VDS to this current equation, and lambda over here is known as channel length modulation coefficient. Keep this in mind that for an ideal MOSFET, we will always use this equation, and majority of the time this is what comes. And so in an ideal MOSFET, drain current will remain unaffected of VDS. However, this only happens after the threshold voltage is met. After that point in saturation region, drain current should remain unaffected with VDS. However, due to channel length modulation, drain current actually slightly increases with VDS, which is very similar to what we had learned in earlier FET. Before we wrap this up, a quick note on how a MOSFET actually works. So basically, MOSFET works same as BJT, So this gate you can consider is the base of the BJT. So it controls whether current will flow in through the gate, through the drain, and then flow out of the source or not. This substrate is generally disconnected in a circuit. Now, what happens is this drain to source voltage, so this voltage we can actually measure as a quantity of VGS, so gate to source voltage minus V threshold at the saturation point. So gate to source voltage minus threshold voltage will give us the VDS saturation. Now generally in terms, VT will be given to you and VGS will also be given to you. Now you would be asked, for a given VDS, will will the MOSFET conduct electricity or not, and if it does, where it will work. So whatever this VDS saturation value you get through this, you can simply compare the VDS given value and see that if this is greater, then this will work in the saturation region, and if this is lesser, then this will work as a triode. So that is how MOSFETs work in circuits. And if we talk about a MOSFET circuit, how it is used, the gate is generally connected to a potentiometer and fed with a voltage, and the source is the drain is connected to a voltage source, and the source drives our load. And that is how MOSFETs are used in the circuit.